Welcome back to the Brainwave. Today we're going to be talking about what is the matter in this world. So we have a couple of main points for the day. First off, we're going to just get to what is chemistry. What are we all made of? Secondly, we're going to talk about what is matter, because matter is what makes up chemistry. Chemistry is what makes up us. And then lastly, we're going to talk about the different types of matter, or we're going to start hitting on the different types of matter. We'll finish that off on Wednesday's lecture. So, first off, let's just do a quick introduction on what are chemicals. A chemical is any substance that has definite composition. And what is chemistry if that is what a chemical is? If all a piece of matter needs is definite composition to be considered a chemical, then what is chemistry? Well, chemistry is the science that is focused on the properties and changes of chemicals. So, chemistry is similar to biology, where biology is the study of life. Chemistry is the study of chemicals and the properties of those chemicals. Now, why should we even care about chemistry? We should care about chemistry because it is literally every single thing around you. You are chemistry. Everything you eat, everything you touch, everything that you have around you, the walls in your room, your face, your glasses, your hair, all of it is made of chemicals. Your entire body functions on chemicals. Let's look at this picture over here at the right and start to break this down. So this big picture at the top is an organism, aka a baby, like you were previously. And that baby, inside of that baby, we have organs. You have your skin, you have your heart, you have your eyes. All of those are examples of organs. And then within those organs, we have tissues. Tissues are basically big globs of different cells. Those tissues contain what we call macromolecules. Those macromolecules then contain cells, the individual cells that control your life. That DNA contains molecules. Those molecules contain atoms. Those atoms are what build up the elements that we call chemicals that run your body. And I've told you guys this already, and we're only on the third day of class. Your body is basically a giant chemical computer. The cells that build up your body and everything inside of those cells are basically just chemicals that talk to each other and then change the structure inside of your body to make your body function. So without chemistry, you would not exist. Now, how this is working is through what we call chemical reactions. So chemistry every single day is controlling and manipulating your body through chemical reactions. So basically, you eat something. Let's say you ate a cheeseburger for lunch. That cheeseburger, when it enters your body, is going to interact with the acid that's inside of your stomach. That acid is going to break down those large pieces of food into smaller pieces of food, like sugars, fats, and proteins, macromolecules, that then can be processed by your cells. Those cells are going to break down those macromolecules into the nutrients that your body can actually process. Those nutrients are then transported through your bloodstream to your organs to give nutrients throughout your entire body, or throughout your entire machine, if you would consider yourself a machine. And there's a bunch of different types of chemical reactions. We're not going to get into them today, but to make it really simple, basically we have reactions where we have A and B come together and they fuse with each other. We have A and B that are already put together and we can break them apart. We have A and B here and we want to add on C. That would basically be the addition of 1. Or you can have A and B and C and D, and you add A and B to C and D. So that would be a double replacement, or a double fusion, if you want to think of it that way. But again, you don't need to know those terms at this point in time. We'll go through that later on. What's important here is to know that chemical reactions are the heart and soul of how you function. They're the heart and soul of how the entire world functions. Now, in these chemical reactions, basically what's happening is we're taking one substance, like a cheeseburger, we're breaking them down with something and turning them into new substances. So these reactions are represented by equations. Just like in math where you have 1 plus 2 equals 3 or 2 plus 2 equals 4, in chemistry we have the same thing, except our equations look a little bit more complicated. We start to add letters into the equations. We also add subscripted numbers. So we might have like a C with a lowercase 6 or with a small 6. You also then can have a 2 outside of them. So like here on the bottom right, you'll see it says 2H2. That 2 is telling us that we have 2 as the coefficient, which means we have multiple of those H2 atoms, okay? Instead of just having one H2, we now have two H2. And H2 is unique in its structure. Again, we'll talk about that later. What's important here is to know that these chemical reactions are basically math equations. So you can read them like a formula, and chemistry is its own language that we'll get to learn over time through this class. Now, all of these reactions have two main parts. They have the reactants on the left-hand side. So if you look at this image on the top, you see we have CH4, which is methane, plus 2 of O2, 2 oxygen molecules that are being added in. And then we have products on the right side. So the products are made by this reaction, by the changes in this reaction. And so out of methane plus 2 oxygens, we get CO2, carbon dioxide, and then 2 H2O, 2 water molecules. And this is the basic structure of how the entire world works. This cup that I am drinking water from, this is a polymer, aka a plastic. This plastic was probably made in a factory somewhere. That factory used a custom-made dye or mold to make this cup. The material that was used to make this cup came from chemicals. Those chemicals were extracted from the environment or artificially produced. And before we had that polymer or that material, somebody had to discover that polymer or that material from a chemical. Okay, so chemicals are the basis for everything you see around you. Now, if chemicals are the focus of this class, why is the name of this lecture, What's the Matter? The reason it's called What's the Matter is because matter makes up everything. Those chemicals that we're talking about aren't just random chemicals. They're not just elements out in the wild. What they actually are basically atoms. Now, we're not going to talk about atoms yet. We'll get to them here in a minute. But the word atom should sound familiar to you. An atom is basically... think of it like a nucleus. You've probably talked about in biology a nucleus, which is basically the brain of a cell. And then outside of the nucleus, you have a bunch of other organelles and materials floating around to help the cell function. Well, matter is very similar, just on a much tinier scale. You'd have to put millions and billions of atoms side by side to get the width of one cell. But what is important here is that the atom is the basic molecule for all matter, or the basic construction block for all matter. So you can think about matter kind of like Legos, where when you buy a new Lego set, or if you've ever had Lego sets in your life, you open the box and you just have tiny little pieces everywhere. And you have to follow the instructions and put them together and crimp them together, and then eventually you build like a house or a car or whatever. Matter is the same concept. Matter is basically this energy. Matter is basically this material that takes up space and has mass. Okay, that's the simplest way to think of it. So matter exists in many different forms, and the easiest way to put it is that it has mass. And we'll talk about what mass is here in a minute, and it also has a volume. So volume is the space an object occupies. So again, with this cup currently is partially filled with water. That water has a specific volume. This water, which is a compound that I am drinking, right, that makes up 70% of my body, is currently occupying a space in this fixed object, which is a glass. So this water is taking up space, which means that this water has volume. At the same time, this water in my cup also has mass behind it, okay? And all mass is basically the amount of matter in an object. So mass is different than weight, and I'll hit on that here in a minute. But to put it simply, weight basically is a measurement based on gravity. So weight is actually a measurement of how much force of gravity is being applied to you, and so weight is relative to whatever planet or part of the universe you're in, whereas mass is a definite measurement of the amount of matter in an object. So the amount of matter of an object never changes, whereas the weight does change. So this water has a specific mass that will be the same across the entire universe. But the weight of the water in my glass is different here on the surface of the Earth than it would be up at the space station. So, a more, maybe an easier example would be a ball, like a soccer ball or a basketball. If I bought a new soccer ball at the store and it was empty, that has a set volume. There is close to zero air in that ball when I purchase it. And then if I go inflate it so I can go play soccer in the yard, now it has an increased volume and an increased mass because the amount of matter in that contained object, the soccer ball, has increased because I've added air, an element or a chemical, into it. So that is matter. Matter is not one specific thing. It is anything, any kind of object that has a mass and a volume. And that is the key property of matter, is that it has to have mass and volume. Now, again, mass and weight are very different. They are related, but they are not identical. So mass measures the quantity of matter. Again, think about the soccer ball example. So the mass of that soccer ball when it is deflated is close to zero. There is no air or very little air contained in that flat soccer ball. Let's go back to that picture over here on the right. So this one on the left here that's partially deflated, the mass of that partially deflated soccer ball is lower than the mass of the soccer ball on the right. And so this mass basically measures the quantity of matter in there. The matter that can be contained in that ball could be anything. It could be oxygen, it could be helium, it could be nitrogen, it could be methane, it could be propane, it can be anything. It just has to be some kind of element or chemical or matter that is contained in there. And matter is the root of all chemicals on Earth. Everything in the universe consists or is produced, exists because of matter. Everything is matter. And that's why I've been telling you guys you are the universe, because you are matter. So if everything else around you is matter, then you also have to be matter. Now, mass is different than weight because, like I said, weight measures the force of gravity acting on an object with mass. So in order for weight to even exist, one of the qualifications for weight to exist is that something has to have mass. So again, I have this cup with water in it, a set amount of water in it. This water has a mass that is the same everywhere in the universe. Okay, so this water, the amount of water in here, is going to have the same mass on the surface of the Earth as well as on Mars, as well as on the moon, as well as in space, and so on and so forth. But the weight of this water will change on the surface of the Earth and on Mars and in space and on the moon. And the reason for that is because weight is a measurement of the force that is being applied to a mass or to a piece of matter based on the gravity. So you guys should know that in space, for instance, we say that space is a zero gravity environment. There is no gravity in space. It is close to zero unless you are spinning or you have some kind of force applied to you. So because space is zero gravity, then technically this water would not have any weight in space. In space, the weight of this water would be zero. It would be floating around. It wouldn't even be contained in the cup. But the mass of this water, if I could contain it, would be the same as it is on Earth. Now you're probably thinking to yourself, well, if weight is always changing, how do we calculate the weight? And it's very simple. The weight is equal to the mass times the acceleration of gravity. So the mass, again, is always the same. And the mass is a universal unit or a standard unit. And this is something that we will talk about how to measure during our first lab. So basically a mass is something that we could measure with a digital scale or with a balance. And we're typically going to measure that in grams or kilograms. And then you take that mass, so let's say this water weighs 40 grams. I'm going to take that times the acceleration of gravity. So in our case, this 40 grams of water would be times 9.8 meters per second, and that would give me the weight of this water. Okay, so on this graphic that I have here, you can see on the left here, we're starting on Earth. And I have a mass that weighs 10 kilograms, and the weight on the scale is 10 kilograms. And then the weight on the Earth of that 10 kilograms is 98 newtons. A newton is a measurement that basically can be converted to pounds, but a weight, but it's measured in newtons because Newton is a force, or is a measurement of force. We will get to that much later in the semester, but basically this is a way of showing you how you can do this calculation and how this would change in different parts of the universe. So on Earth, a 10 kilogram mass has a weight of 98 newtons. On the moon, a 10 kilogram mass has a weight of 16 newtons. So that tells us that the gravity on the moon is significantly lower than that on the Earth. And then in space, a 10 kilogram mass has a weight of 0 newtons because space is a non or zero gravity environment, so there is no gravity to take account of. So then by the simple math of this equation, where weight equals mass times the acceleration of gravity, if gravity is 0, then the weight is 0 because it's a multiplication by 0. Now, matter comes in many different forms. My example here, I've been showing you liquid as water in the liquid state, but water can also be gas. If you've ever been in a steam room or you're familiar with steam and fog, those are gaseous forms of water, and these different forms or states of matter have different properties. So like a solid, for example, over here on the left, has a fixed volume and a shape that are the result of the particle arrangement, and they have a more rigid structure. And so these images on the bottom are just cartoon depictions. This is not what's actually happening in these molecules or in these elements, however you want to think of it, in these chemicals. But this is a way for you to think about it, because you've got to remember that one thing you always have to remember is that matter is always moving. Matter is energy, frequency, and vibration. It will always be moving at all times. If it ever stopped, the entire universe would fall apart, because it's containing energy at every point and every second in time across the entire universe. But matter that is in the solid form is rigid and has a fixed volume. And a specific shape. So let's think of an ice cube, for example. We'll stick with water. Let's think of an ice cube. An ice cube is going to take the shape of whatever tray you put it in when you froze that water and turned it into ice, bringing it into a solid form. And that solid state of matter has specific physical properties that go with it. So for example, water freezes at 32 degrees Celsius. Okay, if you take it any colder than that, it doesn't necessarily change states. It just takes longer for it to change from its solid state into its liquid or its gaseous state. Now, when water goes above 32 degrees Fahrenheit, not Celsius. When water goes above 32 degrees Fahrenheit, it goes into a liquid state of matter. A liquid state of matter has a fixed volume, so the volume is the same as what you would have put in the solid, but now it has a variable shape. And this is because the molecules in a liquid state of matter are going to be moving a little bit faster, and they are not going to be held as tightly together. So they're a little bit more free form, a little bit more flowy. And then once we get to the gaseous stage, which water would turn to a gas at 100 degrees Celsius or 212 degrees Fahrenheit, then we have no fixed volume or shape. The particles are then very weakly attached or attracted to each other, and they move independently at high speeds. And the reason for that, let's think about water, for example. If we were going to change water from liquid to gas, we have to heat it. We have to boil it. You have to boil water. When you boil water, you're adding a lot of energy into that reaction. So you're causing a physical change within that matter. By adding that energy, the energy has to be transformed in some way. It cannot be destroyed. It just can be transformed into a different object. So you're transferring that energy from the liquid water into a gaseous water, causing the particles to move faster and forming a gas, which would lead to the formation of steam. So matter can be in many different forms, all dependent on the environmental conditions, like the physical conditions or the chemical conditions of the environment. Now, with this, matter has many properties, all right? We've been talking about physical and chemical properties. These are the two main types. Physical properties are determined without changing the nature of the substance. So when we're talking about the states of matter, when I change from a solid to a liquid to a gas, the properties of my water do not change, the physical properties. But if I affect the chemical structure of the water, then I'm causing a chemical change to the water, and at that point we are altering the chemistry of the water. So examples of physical properties would be like the color, the volume, the opacity, or the how clearly you can see through an object, whereas chemical properties would be something like the acidity. So I can take water from a pH of 7 and make it basic and take it up to like a 13, or I can make it acidic and drop it down to like a 1, and we'll talk about that more later in the semester. We can also make water reactive technically, so you can electrically charge water, which would change the chemical structure of the water. We could also make Technically we could make water flammable. That's kind of a hard one here. And then we could make water toxic also. So chemical properties basically form a change in the identity of the molecule that is contained, whereas a physical property does not change the molecule that you have in your sample. It just changes the state or a visible characteristic of the sample. Now let's move on to types of matter. So we're talking about matter, which is this very abstract concept of something, an object that has a mass and a volume. So based on that definition, anything in the entire visible universe, the entire physical universe, which we are talking about physical science here, the entire physical universe, the natural world, is matter. But all of this matter consists of little things, invisible things that you will never be able to see with your naked eye, that we call atoms. And atoms are basically the smallest unit of an element that makes up this matter that we've been discussing. Now, these atoms are important because they maintain the properties of an element, and they have a couple of key parts that we need to know about. So just like in a cell, like I said earlier, an atom has a nucleus. And this nucleus contains two very important pieces of its structure. They have the neutrons and the protons. And we'll dive into this later in the semester. But the simplest way to put it is that the protons are positively charged and the neutrons are negatively charged. And these come together to form the nucleus, or the central heart. Think of it like the hub of the atom. Outside of the nucleus, we have what we call the electron cloud, or the electron orbitals. And basically the electrons are negatively charged, so they're creating the balance. So if we think about it as I have the nucleus in the center here, which is my fist, and then we have electrons that basically are floating in a cloud at high speeds, much higher speeds than the protons or the electrons, the protons or the neutrons, and they're constantly just floating around, bouncing through these orbitals, creating a total shape, if you will, which we call the atom. So the atom in this depiction of it is basically a fluctuation in a field. Okay, so let's take it back to the physical world, something that we can understand. Let's think about it like Legos. Okay, so again, let's say that we're building a house out of Legos. I'm not gonna build a house out of Legos with only one wall. In order to build a house out of Legos, I need 4 walls and a roof at a minimum. On top of that, I probably need a base on the bottom. Depending on the side of the house, I might also need internal supporting walls. Those internal supporting walls are like my nucleus. They're going to be the heart of my building. Without them, the center of the building could just collapse. My roof could collapse. And those external walls that are potentially holding up my roof, On the outside edges, like the four outside walls, those are like my electron cloud. Okay, so this is a complicated concept, and if you ever get into quantum mechanics or any other kind of model of the atom, what you'll learn is that none of this basically is the actual way the world works. Everything exists according to quantum mechanics. Everything exists at every point in time, all the time, and that's a condition that we call superposition. You don't need to worry about that right now. This is simple enough for what we need to know. So basically, think of an atom as the core piece to everything that exists in the universe. The atom is what makes up matter. Matter is what makes up chemicals. Chemicals are what make up your body, and your body is what brings you to life. So, the last thing we're going to hit on today is pure substances versus mixtures. So, we've got all these different types of matter, and if you think about every time you've seen the periodic table, there's hundreds of elements on there, and all of those elements can be combined in different ways to form different compounds and mixtures of compounds. So, we have to think about a way of how we can categorize these different kinds of matter. And what we've done basically is divided them into two main categories. We have pure substances and mixtures. And pure substances are basically raw elements. So let's say I just have oxygen, or I just have hydrogen, or I just have carbon. Those elements that we're discussing that we would see on the periodic table, those would be pure substances. Okay, the alternative for a pure substance would be a compound. So when we're talking about water, H2O, that's telling me that we have an oxygen element. Excuse me. That's telling me that we have the oxygen element with two hydrogen molecules. Okay, so they come together and form a compound, H2O. Now, the alternate way to classify matter is into mixtures. So there are a ton of different types of mixtures. We have homogeneous mixtures, where basically everything is the same, they mix together. So this would be like if I took olive oil and mixed it with vegetable oil. Yes, those products technically have different viscosities, they have different chemical properties and physical properties even, but they should in theory mix. Whereas like if I mixed water and motor oil, water and motor oil are totally different mixtures. They will not mix. What will happen is the one that has the higher density will sit below, and the one that has a lower density will sit on top. So they'll basically be stratified, or they'll be in two different layers. And that is what we call a heterogeneous mixture, because they're dividing themselves based on their chemical and physical properties. So with mixtures, we have homogeneous, where they blend together. Another good example of a homogeneous mixture, think of sugar water. Okay, if I take sugar and I dissolve it in water, eventually you do have a point where sugar will separate out, but for a while before the solution gets saturated, the sugar melts or basically dissolves into the water and mixes itself. So that would be an example of a homogeneous mixture. Whereas a heterogeneous mixture, again, would be motor oil and water. The one with the higher density would sink, the one with the lower density would rise. And that is where we're going to stop for day one. I hope you guys have a wonderful day. Thank you for your time, your energy, your effort, and I'll see you next time.